Right. And the research has been going on for some time, collaboration with Francesco Pederiva, currently with Alessandro Ruggiero, and for some time with Fernando Arias. I think you all understand what we're trying to do. We're trying to solve the Schrödinger equation for the at least the first, the lowest fermionic state, which is a highly excited mode. Diffusion Monte Carlo straightforwardly gives the natural ground state. And as you know, and I will demonstrate briefly, the antisymmetric state decays exponentially fast in any diffusion solution. An important point, which you will all understand, but perhaps not in this context, is that the Pauli principle is non-local. The Pauli principle, which enforces antisymmetry in the wave function, is a non-local constraint on the solution. Now, when you apply diffusion methods, you are doing a local operation. So part of the challenge is to combine the local operations of diffusion with the non-local constraint of the Pauli principle. And I think I have a clue as to how to do that, and I will describe that later. For approximations, the fixed node approximation works extremely well. Gives very close upper bounds when the trial functions are good. But I seek, I think perhaps other people still seek, a solution with no uncontrolled approximations. Now, I once talked about solution with no uncontrolled approximations and got an answer which showed that perhaps there's some difference of opinion about what constitutes no uncontrolled approximation. So I've decided to give it my definition, which is two things. One is that there's an error which is computable internally, typically, but not exclusively, the statistical error in a Monte Carlo calculation. It may also be some systematic errors of size extrapolation and the like. And that any errors can be reduced in polynomial computing time rigorously. So you can bound the errors and get more accurate errors with a reasonable amount of computing. Again, for the Fermion problem, it's easy to see that if you're willing to compute exponentially long, you can get errors as good as you like. Okay, so one asks, is the fixed node a controlled approximation? And my answer is no, it is not. In fact, in most cases, you do the calculation and you pride yourself in the answer because it agrees with experiment. So that your knowledge of the error is not generated internally. You might imagine that you could invent a sequence of functions that improve the fixed node approximation, and if you had such a sequence, then perhaps you would be able to satisfy the demand for no uncontrolled approximations. I don't know of any such thing. And in particular, I would say that any method that depends on a basis is almost surely not it is almost surely an uncontrolled approximation, unless you understand how to extrapolate in the basis, which is hard in general. Our approach to this problem is based on understanding the Monte Carlo more than understanding the physics. So we rely on variance reduction methods, we rely on correlation, importance sampling, and on non-local moves. And of course, it's the non-local moves that permit us to connect with the Pauli principle. Is it possible? Well, there's a school of thought that says that it is proved that the many fermion problem is intractable. I don't think that's correct, and I think that I will show you how it is, in principle, not correct. Many sign problems there are many problems with sign problems, and some of them are provably trivial. Some of them are quite hard, but formally tractable, and there are problems that are intractable. Sometime, I think it's next week, Francesco, I will give a talk this week, the end of this week, I will give a talk about another Monte Carlo problem that related to neutron diffusion, that in one approach, the straightforward Monte Carlo approach is provably intractable. On the other hand, a little common sense and a little bit of Monte Carlo knowledge turns it into a tractable problem. In fact, into a problem that converges exponentially fast in computing time.
What's the problem?
So that
can you give the specifics? What's the problem?
That's the problem of neutron multiplication in a reactor,
Mm-hmm.
and estimating the probability with which a neutron chain continues infinitely long. I will discuss it in terms of a trivialized model problem, which can be analyzed analytically and discussed. Okay, so onward and upward, I hope. The basic approach we use is to use pairs of walkers, which carry signs. The solution of the fermionic wave function is some places plus, some places minus, and to represent this, one reasonable thing to do is to have random walkers that carry the signs. We will use correlated diffusion, and I'll explain what I mean by that. The correlated diffusion will permit us to cancel some of the plus and the minus walkers, and that controls the growth of the symmetric part of the solution. Finally, I will discuss what I call the plus-minus symmetry and show that you need to break the plus-minus symmetry, and that in principle, that's very straightforward by using dynamics that depend upon the configurations of the walkers. Okay, so here we have for you the familiar Schrödinger equation in imaginary time. As was first pointed out by Wigner, this is a diffusion equation in which the potential V serves as a generalized creation and destruction operator. In fact, if you think of a nuclear reactor, then the distribution of fissionable material represents spatial distribution of creation of walkers. Walkers create other walkers. And you can think of this equation exactly in that sense. And just as a sideline, it was this analogy that led me to start thinking about quantum Monte Carlo many, many years ago.
Usually we attribute this to Fermi.
Pardon?
Usually I attribute this approach to Fermi, not to Big.
Well,
Because we hear the story about Fermi throwing dice and estimating.
Fermi did a number of different things. He did throw dice back in Rome,
Right.
to improve his intuition about diffusion of neutrons. He was, after all, thinking about the slowing down of neutrons and how slow neutrons would do more interesting things than fast neutrons. Then there was also the Courant-Friedrichs-Levy paper, which shows that a random walk on a lattice generates Green's functions for elliptic operators.
Mm-hmm.
And that was familiar. So that in Los Alamos, the idea of solving equations like the Schrödinger equation by random walks on lattices was around, and Fermi said, how about the Schrödinger equation? In talking about the analog to reactors, I was talking about my own history, which obviously postdates Fermi's history. Anyway,
But who first made this analogy? Was it Wigner or was it Fermi?
that is the diffusion equation. It was Wigner.
What year?
Early 30s. No, I don't remember. Should find out. Useful history. I don't know if we want a detour into the history of Monte Carlo, but you know, the essence of the history of Monte Carlo was the realization that while the analysis of stochastic processes leads to certain equations, differential equations for diffusion, sometimes integral equations, integral differential equations for the Boltzmann equation, that it was in fact useful to turn it around and create a stochastic process that solved a mathematical problem. And that this was an efficient and useful thing to do. And the basic insight is supposed to be Ulam, yes. Ulam, who tells an anecdote in his autobiography. Anyway, of course, given the computers of the very first computers, it's hard to see that Monte Carlo was really very effective. But given the computers of today, it's quite a different story. Okay. So it's useful to write down the first order.
There is a pointer, but if you want a pointer. There is a pointer.
There is a pointer.
Yes.
Behind you.
Behind you, here.
Ah,
Yes.
this kind of pointer. Well, we're talking about historical artifacts.
It's a classical one.
Well, okay, so this is the Green's function or propagator that advances the solution in imaginary time. And the fact that it's positive is useful and helps remind us that this is a diffusion process. The presence of the potential here reminds us that if the potential is positive, then walkers are removed from the system. If the potential is negative, then walkers are created in the system. And in the large imaginary time, you will generate the fundamental mode of this. So if you expand in eigenfunctions of the Hamiltonian, then the solution in large imaginary time converges to the lowest fundamental mode, the fundamental mode. And that is non-negative. And it's, of course, provably non-negative because the propagator is non-negative. The question of proving that the fundamental mode is non-negative seems to be a challenge, but it shouldn't be. Okay. Again, a reiteration of what is familiar to most of you. This kind of calculation can be improved from the point of view of efficiency by carrying out an importance sampling transformation, which in its essence says that you take the solution and multiply it by some trial function, which is a trial function for the fundamental mode, times an exponential in imaginary time. And this is really part of the importance sampling transformation. And you get a random walk with the following structure. And this is due primarily to David. This is due to David, period. A random walker at R is changed into a random walker at position of delta tau times the logarithmic derivative of the trial function plus a Gaussian random vector. And the walkers are branched, one walker turning into more than one or less than one walker, with the multiplicity given by this. And again, quite familiar, if the trial function were the exact function and the trial energy were the exact energy, then this is identically 1 and the walker is preserved. The Monte Carlo is extremely efficient, and your estimate of the energy has 0 variance. So this is a marvelous Monte Carlo. We are going to talk about the non-interacting, the free fermion case. We can take the trial function to be 1, and the dynamics is exact. The Gaussian gives the correct Green's function for any imaginary time.
May I ask a question?
Yes?
Well, maybe it's too generic, but it looks like this is the right place to ask this question. So, in this method that I also use every day, there might be a pathology to the fact that we have an extensive energy when we do the branching. And some people claim that this is an intrinsic pathology of the diffusion Monte Carlo, and it will never be capable to simulate huge systems.
Simulate what?
Huge systems. Because here we have fluctuations of the number of walkers, and the amount of fluctuations is related to an extensive quantity. We have
It
total
is,
energy.
yes.
So if we want to simulate a huge system, very large number of particles, then we will have problems, unless we have an extremely good tribal function. Do you agree with this concern that diffusion Monte Carlo
I
is
have no
correct?
comment about it. I haven't thought about it. I can see that, yes, if you had a poor function, you might have some problem. I can conceive that. I don't know what the nature of the difficulty would be. David?
I know what he's talking about. I don't know.
Okay, Cyrus. So David, come on, someone help me.
The point is,
Right.
yeah, the point is, if you have a bad wave function,
Yeah.
or a certain quantity of wave function where you go to larger systems, then of course the fluctuations increase. Then you reach a point where your branching is happening so much
Yes.
that all your walkers get correlated.
Yes, I
So
understand.
so
I
when you have a
understand.
population of walkers, you essentially still have one walker rather than a lot. And so
Well-
then the cost goes up dramatically
Yeah.
when you reach that limit.
Right. So if you have very large branching and some stringent population control, yeah. But I don't know what about the trial function would make it worse or better. I think that's the real question.
But the point, it's a scaling question, all right? It's like, take a certain wave function like the best Slater-Jastrow wave function, and then scale to larger and larger systems
Yes.
with that same wave function, right?
Yes.
Then eventually you reach the point that Cyrus is talking about. Well, you have to ask the question, what size of population is going to be adequate? As n goes to infinity, the population size is going to have to go to infinity also.
Okay.
And that comes back into your controlled
Yes.
approximations.
Yes.
And there is an issue there.
There is an issue.
Yeah. I mean, but I think it still ends up polynomial, but it's worse than, instead of being n cubed, it becomes n to the higher power, right?
Are you saying you have to introduce many-body features in your trial function to avoid this?
I'm saying,
That we
no,
always
don't consider that. Consider the trial function as fixed as the system gets larger.
Yeah.
What makes you believe it's still polynomial?
Well, I think if you analyze it, it is. I mean,
There's one
there is
paper on it,
a
right?
little sketch of analysis in one of
So
my
Nemec
papers.
in his paper claimed it was exponential.
I think that's exponential if you're not considering the population size. Well, I don't know.
The time step should also enter, right?
Yeah,
You
the
should
time
tell
step enters
time step
also.
carefully to do this analysis. In general, of course, you want to decrease it as you.
Yeah, on the other hand,
No. I mean, if you're doing accept reject after each electron move, you don't need to reduce.
Well,
the
in this
density.
case, if it's growing, clearly you do want to decrease it. The matter is, I guess, with all these different variables, how do you optimize it? And when you do, what kind of a scaling comes through?
of course,
And they're only in the exponent, so it's possible that a small difference could cause a dramatic effect.
it doesn't
That step has to be factored in the analysis.
doesn't help to take a time step that grows exponentially small.
No, it
Yes,
doesn't
but
grow
it's
exponentially. It grows like 1/n. I mean, it decreases like 1/n.
Yeah.
I mean, either you increase the population or you increase the time step.
Yeah.
But the cost grows the same
Right.
way, essentially. Oh, sorry.
I declare we finished that.
We can come back to it in just a
It-
minute.
Yeah. Okay. And again, quite familiar. Within this context, we estimate the energy by computing this quotient. And I write it this peculiar way because we're going to do it differently. All right. Nobody here needs this, but I will remind you again that the Pauli principle says that the wave function changes sign under exchange or permutation of like spin particles. We're working, of course, within the non-relativistic limit. And that this Pauli principle is, again, non-local. So that we have two issues here. The solutions are not everywhere positive, and we're going to deal with it by introducing walkers with signs. When we do that, I'm assuming that now our population is of pairs of walkers RK plus and RK minus, and our estimate of the energy is replaced by this quotient. So minus walkers simply mean that you subtract their contributions to quantities of interest, in particular the energy quotient, whereas for positive walkers you add. So it's simply a matter of this algebraic sum. But the algebraic sum is extremely important because if the asymptotic distributions for R plus and R minus are the same, then the average of numerator and denominator will be 0. This will contribute the same on the average as that. This will contribute the same on the average as that. And we get asymptotically 0 over 0, which is a reformulation of why the fermions have a sign problem in this new context. We'll call the method statistically stable if the average denominator is not 0. And to make it not 0, we must break the dynamical symmetry that would otherwise give the same distribution for plus and minus walkers. And we need to limit the growth of the symmetric contribution so that, again, it does not dominate asymptotically. Let me make a comment, which should be in this talk somewhere but isn't. I say I want a method with no uncontrolled approximations. And one of the implications is that I can reduce the errors, including the sampling errors, in polynomial time. That means I have to be able to continue the Monte Carlo as long as I choose. And the Monte Carlo has to continue to be stable in this sense. So that a method which is stable for a while and then goes unstable might be useful, might be a very good kind of calculation, but it does not qualify as no uncontrolled approximation. So we need long-term stability, indefinite stability to satisfy this concept, and that's an important point, and not at all a trivial point. Okay. Okay, back on familiar grounds. I've gone back to the eigenvalue expansion, and I single out the two terms which are the symmetric ground state and the lowest fermionic state. And I notice, as you already know, that this decays faster than this, so that unless you do something special, as you continue indefinitely, the information you get about the antisymmetric part grows exponentially small. You are not stable in the sense that I want it. And again, one can defeat the decay by growing the population of walkers exponentially fast, demanding exponentially growing computer time. And we're not in favor of that. Furthermore, and this is well known, that as the system gets larger, then typically the energy gap between symmetric and antisymmetric grows, in many cases as the number of particles, so that the exponential decay is exacerbated. The problem gets worse and worse. So it's challenging both in imaginary time and in system size. And I've said this before, it's worth saying again and again and again. The Pauli principle is a non-local constraint which has to be reconciled with the local character of the kind of random walk implied by diffusion Monte Carlo. I don't think I need to discuss this. Okay. The first thing that's new about, well, the second thing that's new about our general approach is, the first thing is that we use pairs of walkers. The second thing is we correlate the diffusion of the pairs of walkers. And in particular, you will recall, oh, sorry about this. You will recall that one of the crucial steps in diffusion Monte Carlo is that you add a Gaussian vector. So when you have a pair of Gaussians, a pair of walkers, you need two Gaussian vectors. Now you could make them independent of each other, in which case you would be doing just two walks at one time. We correlate them. So if U plus is the vector for the plus walker, then we write down a U minus, which is calculated in this form, and I will show you this geometrically in a moment, which reflects U plus in the perpendicular bisector of the many-dimensional line that connects R minus and R plus. That means that the Euclidean distance between the walkers undergoes a random walk in one dimension. That random walk is guaranteed for the systems of interest to us. That random walk is guaranteed to meet at zero. So sooner or later, these walkers are guaranteed to meet, and when they meet, they cancel. A plus walker and a minus walker in the same place have asymptotically no contribution to anything in the future calculation. They don't contribute to the antisymmetric estimators, they don't contribute to any symmetric estimators, and they do not contribute to the population. So the population growth is controlled also by this process.
What do you mean by linear time?
Pardon me?
The diffusion distance goes as the square root of the time, right? You wrote linear
What
time.
grows as the square root of the time?
The diffusion distance.
Yes, that's right.
You have in red linear time. I'm just wondering what linear time means.
Actually, I will show you more about the time distribution. If they were free diffusing, if you had a free diffusing particle in one dimension on an infinite system, yes, it would diffuse away. But these systems are constrained. For example, periodic boundary conditions mean they don't diffuse to infinity. They're guaranteed to meet. A potential, and I will show you how they meet in several systems with different potentials. Very important. That's a good point, and you gave me the opportunity to make an important point that I should have made. All right. This is the picture I'm talking about. You have a plus walker and a minus walker, and we generate a Gaussian vector for the plus walker, u plus. And we generate the Gaussian vector for the minus walker by taking this u plus and reflecting it in this line to get that. Okay. And now we say, okay, the plus walker carries a certain amount of weight with it, given by the Green's function, simply given by the Gaussian. So that spreads the plusness all around. Meanwhile, the minus walker is spreading minusness all around. They exactly cancel on this line, and plusness dominates on this side, minusness dominates on this side. Put another way, when you put these two together and sample the Green's functions this way, future plus walkers will exist only on this side of the line. Future minus walkers will exist only on this side of the line. And the cancellation is part of the cancellation that controls the population.
Can I ask a question?
Yes?
That line, in reality, it's curved.
Pardon me?
That line, red line, it's curved, it's not straight.
No, it's a straight line.
It's a nodal line.
Pardon me?
It's the nodal line.
No, it's not the nodal line.
Interacting.
Excuse me, it is a nodal line. It is the nodal line that constructed from the Green's function centered here minus the Green's function centered here. This is a nodal line for Green's functions, not the nodal line for the wave function.
But it doesn't have interactions in it.
This does not have interactions in it. And we don't, as far as I know, we don't need to have interactions.
Time, that line?
Pardon me?
It's fixed its position in time?
No, wherever these are, these wander around.
No, but the position of the red line.
As these wander around, in particular, then the position of the red line wanders around.
Well, no, but for free fermions, it will stay fixed in.
No, this does not.
These are red ones.
This is not necessarily for free fermions only. I'm assuming we're working within the framework of diffusion Monte Carlo, and I'm talking about the Gaussians that you use in diffusion Monte Carlo, and those are just Gaussians.
No, I understand, but if there is no drift, if there's only
if there is drift, then this one drifts and this one drifts, and we recompute this geometry.
If there's no drift, then that line is fixed in time.
That's right. If there's no drift,
For this particular pair.
that's right. If there's no drift, then these move parallel to themselves. As a matter of fact, in harmonic interactions, they move parallel to themselves as well.
When you initiate at the very beginning, do they start at the same point and go out?
No, you can start this process in various ways. The easiest thing to do is to start by sampling plus walkers from a trial distribution, or the plus part of a trial distribution, and generate minus walkers by permutations. And, okay.
So the red line is a hyperplane, or
It's a hyperplane.
Okay.
Yeah.
I
But
don't see that the diffusion is going to bring the two together.
Yes.
Depends on the direction of you.
It's a one-dimensional walk.
It's a one-dimensional.
I mean, this move they went.
The walk I'm talking about is the walk that connects first this point and this point, and then this point and this point.
Yeah, and the way you've drawn it, they're farther apart.
On this particular move.
That's true.
But it's a one-dimensional walk, they meet.
Oh, I see, just because in any one-dimensional problem.
You're going to cross the
they
origin.
meet. Okay.
Yeah.
Okay.
That's a key insight here. Yeah. Okay. Here I've tried to exhibit the idea of cancellation a little more vividly. Again, here's the original plus walker, the original minus walker. Here is the step for the plus walker. Here's the step for the minus walker. And we construct the strength of the density of walkers at this point by calculating this Green's function and subtracting this Green's function. Similarly, we calculate the strength, negative strength of walker here by calculating this Green's function and subtracting this Green's function. Or rather, subtracting this and adding in this Green's function to give a negative result here, positive result here, 0 on here. Okay, so again, there's no positive density on this side. There's no negative density on this side. So this is Fernando's work, in which he calculated, actually, Kevin said the question, okay, you cancel, that's great, but how does it depend on the number of particles in the system? If it gets slower for many particles, you're worse off.
That green function you showed in the previous slide, does include the interaction or does not?
Including?
The interaction.
No.
It's only the free propagator.
This is the free propagator, yes. Again, that's all you need in the framework of diffusion Monte Carlo.
No, you need the weight you pick up from the potential too.
Pardon me?
You need the weight you pick up from the potential too.
Oh, that goes into the branching.
Yeah.
And these walkers may branch differently. What am I doing here? Yeah. If you have a potential, and it's not a harmonic potential, then when you get here and you get here, you have different branching. Right. And so you may have more of this than of that. And if you have more of this, I was going to get to that, but you ask now. If I have a little more of this, what I do is I take the minimum of the two weights and say I have a pair with that weight. I take the leftover weight and I symmetrize. I take that walker and a similar walker produced with a negative permutation, with an odd permutation, and with probability 1/2, create that pair. So I can follow the weights required by the interaction and still preserve the structure of the calculation as an ensemble of pairs. Okay. So for a free fermion system, in 2 or 3 dimensions, Fernando calculated the time to cancellation as a function of the number of particles. And as you see, it's essentially constant. So large systems are not a challenge for this. We were planning to work with the Porsteller
You want to
potential.
make that more intuitive for us? I mean, that's a surprising result. Your previous view graph is a surprising result.
Why does that surprise you?
The cancellation time doesn't depend on size.
I mean, like there's they're non-interacting particles, so you just
Yeah.
compare something's random in space, and there's just a finite amount of time till they hit each other.
No, but
We're going to the diffusion constant, right? In this case, it's for each pair in this case.
I mean,
Okay, when we did these calculations, we kept the density constant. We kept the density constant and, of course, increased the box size. Is that right?
Yeah.
Yeah. So,
Basically, it's controlled by the average interparticle distance.
pardon me?
It's controlled by the average interparticle distance.
Yes.
this time.
Yes, yeah.
So that reason should
So it would change with density. That
Yeah,
number.
yeah. For the Posh-Teller potential, the time to cancellation decreases with the number of particles, because the potential in the ground state tends to pull the system together and encourages the cancellation.
So does this mean that for a
Did we not do, I guess we didn't, I
repulsion-
don't show, Fernando did a system of harmonic potentials put together to form something like an atom, and the time to cancellation was decreased with system size even faster. Again, for the same reason. The potential pulls the particles together, tends to make them closer, easier to cancel.
So that's because the system collapses actually?
Yes.
By density state?
Yes,
Yeah.
yes, exactly. So the system wants to collapse, and of course the cancellation works against this collapsing. Okay. And this is the crucial consequence of using correlation and cancellation. Okay. Now we come to another essential point that took me some years to grasp. What we're talking about is that we have a distribution, a joint distribution of plus and minus Walkers that is going to evolve in time. And as I told you earlier, if the marginal, I didn't say it this way, but if the marginal distribution for the plus Walkers is the same as the marginal distribution for the minus Walkers, then the energy quotient will be asymptotically 0 over 0. So we have to prevent that. Now, if you imagine that the evolution is controlled by some operator of this kind, and that the operator is invariant under exchange of the plus and minus coordinates, then asymptotically, the fundamental mode of this equation will be invariant. And in the limit, well, that's what I'm saying here. In the limit, the infinite imaginary time distribution of plus and minus will be the same as the infinite time minus and plus, and the energy quotients will vanish. That is what I call the plus-minus symmetry. And the question is whether the dynamics for the plus are the same as the dynamics for the minus. Or another way of saying it is this. Imagine you have a system of plus Walkers and minus Walkers, and you magically interchange the labels. You relabel the plus ones minus and minus ones plus. And the answer is, does your random process look the same? And if it does, then you will have this plus-minus symmetry. You will have an unstable Monte Carlo, in the sense in which I've defined it. Yes?
So, can I see, I mean, in 1D, obviously, this is stable. Cancellation is perfectly stable.
In 1D, it's stable.
So can I see what about 1D doesn't work in the argument you've just
What
made?
is stable about 1D is that if you start with a population of Walkers in which the plus ones are to the right of the minus ones, and you do this kind of correlation and cancellation, that geometrical property is preserved. The plus never cross the minus.
So I agree, but you've just now made an argument that if the plus-minus symmetry is not broken, that this doesn't work. So
Well,
just see where,
there the plus-minus symmetry is broken by construction.
just by the geometry.
Yeah.
By the initial condition, right?
Pardon me?
You set it up
It's
to be
also
an
broken
equal-
in the initial condition
Yes.
in 2D too, right?
In
but-
2D,
Of course, you lose that eventually
Right.
from stochasticity as you move.
that's right.
Yeah, in 1D, if you initialize it by breaking symmetry, the symmetry is
Right, so I understand why it works. I'm trying to understand why the
So
argument
it's
plus
really
minus symmetry
ergodic
can't breaks down.
question. In addition to that, you have
Because
to
they
say
can
something about
exchange
the
without
ergodic
going through each
nature
each other.
of the process, right?
Yeah.
Right? The
Yeah,
ergodic
it's-
nature, right?
It's really that in 2D stochasticity lets you.
Yeah.
Right.
It lets you
There
break this
exists a
stuff.
pathway.
lets you go
for
past each other.
fluctuations
Okay, I'm about to break my vow of. When I first started thinking about this, I thought about 2D, in fact, and thought about walkers in a circle. And under some circumstances, they would just, if you put the plus ones on the right and the minus ones on the left, they would diffuse around and mix up. And I said they'd rotate around each other. And I said that in the talk. And a certain wise guy, David Sepperly, said they don't necessarily rotate around each other. And I knew I had to think about it a little harder. And well, what was needed was simply some more general words about symmetry, plus minus, the symmetry of the dynamics under exchange of the plus and the minus. So, can we break it? And the answer is, in principle, yes. We look at the dynamics and we ask questions. Is the plus walker in the plus pocket of a trial function? Is the minus walker in the minus pocket of a trial function? If so, use this kind of dynamics. If not, use those kind of dynamics. That, generally speaking, makes the dynamics, breaks that symmetry. Unfortunately, it doesn't necessarily give you very, very stable results. And I think that's part of the difficulty we are facing.
They are stable but noisy.
It's unstable but very noisy, yeah. So here's an example. You might, if the plus one walker is in a plus pocket and the minus walker is in the minus pocket, you might choose to use the same u plus. Use u minus equal to u plus instead of reflecting in the hyperplane. That tends, this pair is going to contribute good things. Keep it alive. Remember, I showed you the time to cancellation. And if a pair has a long time to cancellation, if a pair is a good pair contributing positive things to numerator and denominator, you want to keep it alive. If it's a bad one, you want to cancel as soon as possible, and you have that opportunity. Okay. I've referred to this before. It's very important. We call it repairing, and it is really the heart of how one contends with the Pauli principle. If P is an odd permutation, then the descendants of a Walker at R plus have exactly the negative of the expectations, weighted with an antisymmetric function, of the descendants of P R plus. Is that obvious? Do I need to explain it more? There are two ways to explain it. And maybe I should have more about it. Bob, shall I explain it more?
The significance hasn't sunk in yet.
Pardon me?
The significance is not sunk in for me yet.
Has the truth sunk into it?
That sounds very plausible.
All right. If it merely sounds plausible, I will explain. There are two ways to explain it, as I say. One is what I call well, never mind. You start with the eigenfunction expansion of the delta function. Okay? And then you apply many Green's a long-time Green's function to it. what you get in the, and then you weight it with either the symmetric function or an antisymmetric function. In the limit of large time, large imaginary time, what you get is the ground state wave function times a symmetric function, if that's what you're weighting with, at the point you started. Similarly, if you're weighted with an antisymmetric function, you get the overlap of your antisymmetric test function with the ground state antisymmetric function at the starting point. Okay? Now, if the two starting points differ by an odd permutation, then that expectation simply changes sign. Okay. The other way of looking at it is to say that if you start with a walker at point R, and in the long term you're going to weight it with an antisymmetric function, and then you go to a permuted place, permuted with an odd permutation, you can look at the forward, you can look at the path from where it starts to infinity, the two paths. And the point is that you can map the paths one to the other using the same permutation. Therefore, the answers are identical. The expectations are identical, except for sign. Okay, so if I have a walker at R, and I contemplate introducing a walker at PR, where P is an odd permutation, and assigning a negative weight to this new walker, then the sum of these two expectations are the same. So half of that preserves expectations. Now this is exactly the same as the anti-symmetrizing operator. If you want a function psi of R and you want to anti-symmetrize it, you apply 1/2 psi of R plus 1/2 psi of PR, where P is an antisymmetric permutation. And that's exactly what we do here. So we built into the Monte Carlo an anti-symmetrizing operation, which is non-local. The permutation steps of the Monte Carlo are non-local steps. And I claim that this is one way of combining the needs of a diffusion-like process and the Pauli principle. And another way of putting it is that it's the spookliche Fernwirkung that Einstein talked about. Okay, and here's another calculation that Fernando did. Calculated the time to cancellation as a function of the separation of the Euclidean pair. And as you see and would expect, it vanishes linearly as the pair gets closer and closer together. So close pairs cancel quickly, distant pairs cancel more slowly. Imagine that. So we can, again, adjust the cancellation time by choosing different permutations, which is another way of breaking the plus-minus symmetry.
What potential will these be?
Pardon me?
What potential will these be? What potential?
This is free. Free fermions.
These are free fermions.
So then why doesn't the time grow quadratically with the distance?
I mean, why does it bend over?
Why is that? I would expect the time. I assume the y-axis is the time to cancellation.
Yes. Can't you see the T there?
I could have maybe 20 years ago.
I apologize for the quality.
But my question is, we know that the diffusion distance grows as the square root.
But this has a drift velocity.
Well,
No, there's no
that's if
drift.
there is an
There's no
external
drift.
potential. He said there is
No,
not.
no, it has a drift from that thing that forces.
Oh, right, right, right.
Not from the potential, but from
Still one d.
mirror potential or whatever you call it.
Right, no, but that's just a one-dimensional random walk. I mean, that distance just goes as
Oh,
the
you
square
mean-
root of
You
time.
mean, what
Yeah,
about the
but-
other dimensions?
But you know, this is,
No, no, but
well.
I think I need to just consider the one dimension, but that distance of the two particles just goes as the square root.
yeah, but you are changing the nearest neighbor.
What?
He's using
You are-
second quantized notation.
Well, that was a reference to my talk. Never mind now, you were there. Sorry, what?
I know what you're saying.
The pair is formed by exchanging a couple of particles, and they are the two particles that are near each other.
Nearest neighbors.
Yeah, nearest neighbors.
Okay, but once you form this pair, you're talking about the cancellation of this pair, right? You're not talking about forming other pairs.
Well,
Wait a minute. We're talking here about diffusion in the presence of an absorbing.
Well,
It's not free diffusion.
the absorption is only when the two particles.
That's
meet.
right.
yeah.
Yeah. But,
Do you change the pair at all at any point while they're propagating?
pardon me?
Does the pair change while they're propagating at all? Is at any point in this free fermion example, who I'm paired with change as a function of imaginary time?
Haven't heard the question. I
Sorry.
apologize for my
Who
hearing.
you're paired to, does that change as a function of imaginary time?
No.
So you repair once, and that's it.
Yeah, yeah.
So, I mean, I still don't have the answer to my question, right? I mean, if I start a certain distance apart, I want them to meet, right?
Yeah,
So they have to diffuse a certain distance d.
yeah.
The time to diffuse that distance goes as d squared,
Yeah.
right? And so I would have expected the
Uh,
time to look like a parabola, instead of which it's curving the other way. And so I don't understand the shape of this.
I
Yeah, but what happened is that.
can't answer your question
It
now.
would be in the case that you exchange a couple of particles at random. Because what happened.
No, but you formed a pair, and then you're keeping the pair fixed, right?
Yeah.
So you formed a pair at this distance d. Now we are talking about how long does it take for this pair to meet, right? It has to diffuse the distance d.
Right.
Yeah.
Okay, we can leave it to the discussion.
Yeah.
So
Okay.
I don't want to
Yeah.
take too much.
I'm almost done. Oh, yes.
Aren't all antisymmetric
Here's another.
possibilities taken in these calculations?
Another possibility.
Aren't all antisymmetric possibilities taken for the cancellation in these
Cancellation.
No, when you change from positive to negative, but when you look at all of, you don't.
He's not, so he's not using.
He's not using second quantized. Okay, so I take it back.
Yeah.
Okay. Again, another form of making the dynamics depend on the configuration. Again, another way of breaking the symmetry. Oh my goodness. Finally, it's clear that just breaking the symmetry is rather inefficient, and some kind of improvement is needed, and we have relied on what we call second stage importance sampling, in which we define a function which predicts the future contribution of a pair to the denominator of the energy quotient. That's the point of view we have taken. And here's the denominator. And in fact, if you were doing for example, a fixed node or a pair of fixed node calculations in which the plus walker was on the plus side of its trial function, and the minus were on the minus side of its trial function, then this, in fact, would be your prediction of the future contribution. Again, by the argument that derives from the expansion of the delta function in eigenfunctions. And so when a pair is a very good pair with a plus walker well inside its pocket and the minus walker well inside its pocket, we would expect the importance function to be precisely this. For two-dimensional free fermions, we've introduced a lousy trial function. We were challenged to do that. And this is it. We just mix in a little bit of higher orbital, and you can get very bad trial functions this way. So our second stage function is some function of the denominator, and we would expect it to be linear, certainly in this regime, possibly continuing to be linear. And we don't really know what it is here, so out of our ignorance, we define it to be 1. We're saying that any pair in which the positive is in the wrong, well, any pair in which both walkers are in the wrong pocket has some chance of being moved around and becoming good for the future. Obviously, we can't define it to be 0, and we're reluctant to make it go to 0 because we don't understand how. By the way, when you do importance sampling, one of the rules of thumb is never underestimate the importance function. Because if you do, then you will get high weight answers and high variances. Whereas if you don't, you'll just get somewhat poorer statistics. So the dynamics of stability include, well, for interacting systems, we would have our first stage importance function, which drives Walker to the maxima of the symmetric function. We will correlate the Gaussians to bring plus and minus walkers together. We'll cancel walkers when they meet. We'll repair with permutations and do this in various ways to break the symmetry. And then we'll apply second stage importance. And as far as we can tell, this ought to be exact and stable, except for population bias. And the fact is that while it is stable and statistics are reasonably good, we do not get the right answer. We're off by anywhere from 0.5% to 1% in the energy of a free fermion system. And why that is, we do not know. It is possible that that we're handling the population control in a naive way. Although in the code there are several forms of population control, and they doesn't seem to matter. Rudimentary experiments of increasing the population by a bit don't seem to help. So at the moment we're at a loss. So, yeah.
So does the bias depend to the choice of the second stage importance function?
We play with that a little too. Doesn't seem to matter.
See a changing of the bias?
What the problem is that without second stage importance, stability is very hard to see.
I understand, but if you change the second stage from 1 to -1, or I forgot, but the slope of that line
Yeah.
that you draw.
We change the slope and it doesn't do very much. Doesn't change.
In the sense that one might just say, okay, let's try to use some slope and then reduce it. And see whether possibly you extrapolate something.
Yes.
Okay, the point is that if the slope is large enough, that the efficiency is such that you see numbers with a decent variance, the bias is large, quotation mark, in the sense that it's outside of the statistical error, definitely. When you decrease the slope, obviously the efficiency gets worse and worse. So your error basket gets large. So you don't extrapolate anywhere. That's the point. So yes, there is a change, but it's useless at the moment we cannot make any use of this change.
Have you tried to calculate that second stage importance function as a mixed estimate without doing that?
I'm sorry, what's the question?
If you take the naive DMC without the second stage
Yeah.
importance function, and then you calculate that importance function as an operator, and then you have a guess on how that should be.
Oh.
And then you iterate these few times to optimize that.
That's very hard. Remember, it depends on the coordinates of both both walkers.
No, I understand. But
So
maybe this could guide you to see it.
for a 10-body system, it's a function in a 20-dimensional space. If we had some better conjectures, I invite you. Invite everybody. Send in your conjectures. There's a prize for the best one.
But you could, if you fix a form, like somebody was saying, changing the slope. So if you define a functional form,
Yeah.
then you could use this to estimate which one is better.
No.
By calculating.
Yes, although.
What does it mean better? Because
But if it's just one parameter, I think it's easier. I think it's easier just to run the calculation with 2 parameters and see what happens.
But you tag you follow one of the walkers, and what you defined for me, like how you follow it through the random walk.
Yes.
And estimate.
Yes.
And now you could do that with calculating.
Let's talk about that more later. Bob, Robert.
This will be a change of pace question. If anybody else wants to continue that first, they should. Okay, this is probably a really dumb question, but
There are no dumb questions.
I'm thinking of R here as a continuous spatial coordinate. But can it
You
be
are
a mix
correct.
of
In our work, R is continuous spatial coordinates. It is possible to contemplate R being on a lattice.
I was going to say a mix of continuous space and discrete symmetry like spin that might be changed by the potential.
One can, at a very casual level, like me answering your question, say, sure.
But you haven't worried about that
No.
aspect yet.
No. Yes.
You said that you can take a walker and replace it by a walker and one of its permutations.
Yes.
The original walker has a weight of half, and the new walker has a weight of minus half.
Yes.
So that is correct if you're not using importance sampling. If you are using importance sampling with an antisymmetric function.
If you're using importance function, you have to take into account the ratio of the functions, and we do. Yes.
Yes.
Okay, so then you actually get if you're using an antisymmetric function as your importance function, then you will actually
You
get
don't use. Sorry,
plus half
you
and
do
plus
not
half.
use antisymmetric functions as
You're
importance
using a
functions.
symmetric function, and that's why you get
Importance functions are not allowed to be negative. Okay.
fine. Well, we can discuss that later. Okay, but I understand. You're using a positive importance function.
Okay.
And so then I understand what you're doing.
Okay. Okay. I declare this talk to be over. You were right, Francesco. It got a lot of discussion.
But it will be more in the afternoon, in any case.
Okay.
Are there more questions? No? Okay, so we can just meet at 3:30 in room C520. Which is 2:30?
2 1D fermions.
Yeah.
put them on a grid, like park on a well, but just grid up space.
Yeah.
And do all this stuff, look at everything, analytically.
Yes.
And see, where things go wrong. Like,
Right.
should be able to do that exactly.
And 1D, yeah.
Two fermion. I mean, presumably if you have...
What do you mean? You mean two particles?
Two particles, antisymmetric, in a well or some... And just see, plot all these things out, see
Do
what they look like.
You can do the harmonic oscillator trivially.
Sure, I mean, but this all works with harmonic oscillator. You're saying.
Sure.
Okay,
Sure.
so it's only when you introduce.
But I think 1D will not give us any insight. It's going to work.